Hello everybody. Today we're going to talk about Unit 1, Lesson 1 in our interactive calculus notebook. And we're going to start off with an informal definition of a limit and the limit notation. So this limit notation is going to be very different for us. And this definition of the limit is going to be an informal definition of a limit, as the formal definition uses epsilons and deltas. And for this particular course, an informal definition will suffice. So here we go. Given some function f of x and the real numbers a and l, it's important to note that the a and l are real numbers, numbers that you can touch on a number line. This is our notation for the limit. The limit as x goes to a of f of x is equal to l, and that's how you read that. The limit of f of x, that's the lim, is the limit of f of x as x approaches. X arrow a is the x approaches a, and then equals L. The limit of f of x is equal to L. So what in the world does that mean? Well, let's investigate that. The limit asks the question, what does the function value get close to? I could actually say, what do the function values get close to? Or what does the function value get close to as x gets really close to a number a? And the key about limits, which is difficult for first-year calculus students, is to understand that we don't worry about what the function value at a is. Only what the output of the function gets close to, only what the function values get close to. So let's do an example of this particular definition. Here we go. Here I have the limit as x approaches 2 of f of x equals 5. What this says, the outputs of the function f of x get really close to 5 as the x values get really close to 2. So let's look at the graph and consider this graph is a demonstration of this limit. So here I have the limit, just repeating what I have, as x goes to 2 of the function f of x is equal to the real number 5. And this particular graph right here, we're going to let this graph be y equals f of x. And of course, this is my x value too. What this limit says, as the x values get close to 2, from the left and from the right, and we'll discuss those right and left-handed limits, as x values get really, really close to 2, what do the y values get close to? So if I just take this x value and I shoot up here, let me do a line. This might help with the line. Let me do a very light line here. If I take this x value right here, that's the function value for that x value. But if I take this line and I move it, what do those function values get close to? You notice those function values are getting ever so close. And here I'm just, the x values are getting close to 2. And those function values are getting close to this line, this horizontal line here, which is 5. They're getting close to that horizontal line. Whoops, I grabbed the wrong thing. I grabbed the image. Okay, as I get close to 2, those function values are getting close to 5. In the same way, if I came over here, if I'm starting those x values, and they're getting close to 2 down here, what are the function values getting close to? Well, the function values are getting ever so close to this 5 here. Grab the wrong thing again. So I want to be able to grab this. There we go. Now I can grab this. Set her up there. There we go. Okay, so, and the other thing you have to note about this is an open circle. And sometimes the graph doesn't show it. Here's a closed circle. And we have to make note of the difference, because we're going to see lots of graphs of open circles and closed circles. This closed circle right here, this guy here, let me get this line out of here. This point right here represents 2. Well, that was freaky. Bear with me here a minute. Okay, here we go. What this point there, what this closed circle represents, that represents 2 f of 2. That point is actually on the graph of f of x. That point is actually 2, 1. So f of 2 is 1. So we're going to make the note, oh, we did make note of that f of 2 is equal to 1. The actual function value at x equals 2 is 1, but that's not what the limit goes to. That's not what the function values go to as x goes to 2. As x goes to 2, the limit as x goes to 2 of f of x is equal to 5. And this is my 5 right there. So take a minute, think about that. And let's go to our second example here. Example 2. Consider the graph of some piecewise function and use the graph to evaluate the limits that follow. So this is, again, this is going to be my graph of y equals f of x up here. And I have some closed circles and some open circles. But you see most of the closed circle are actually on the graph. This point right here, and I'm going to label this point is going to be -3, 3. And that's on F. And this is going to represent an open circle. That's an open circle. And I want to ask myself some question. The limit is x goes to -3 of f of x. So as x goes to -3, let me get a pointing tool here. And I can just use that yellow one. As x goes to -3, what do my y values go to? So as x approaches -3 here, as I'm approaching -3 from the left and the right, as my x values get close to 3, what are the function values getting close to? Well, we can see they're not getting close to 3. The function values are right here. Here are the function values. They're getting close. They're starting here and they're getting close to -1. They're approaching -1 right here on both sides. So as x goes to -3 f of x, that's the function values get close to -1. And we say the limit as x goes to -3 f of x is -1. All right, let's go to the next limit. The next limit is the limit as x goes to 2 of f of x. Where do the function values get close to? So if I'm getting close to 2 from the left and from the right, where are the function values going to? Well, here's my function, and the output is like, here's my function. Where are those outputs going? Well, those outputs, are they not? They're getting ever so close. The y values, the function values, are getting ever so close to 0. So the limit as x goes to 2 of f of x is equal to 0. Last limit here, the limit as x goes to 3 of f of x. Let's erase this stuff here temporarily. And let's figure out what this limit is. As x goes to 3, from the right and from the left, and we'll talk about right-hand, left-hand limit in a minute. As x goes to 3, what do the function values get close to? Well, if you notice, if I'm right here, the function value is there, and the function values get ever so close. What do the function values approach this right here? And we could make that, it's not an open circle, it's part of the graph, but as x goes to 3, you see the outputs. What did the outputs get close to? The outputs are going to get close to 1, and as I approach 3 from this direction, the outputs again are going to get close to 1. So we say this limit as x goes to 3 of f of x is equal to 1. Okay, and what we're doing here is we are actually evaluating limits graphically. And we're going to learn a couple other ways to evaluate limits, but we're doing these limits graphically by looking at the graph and evaluating these limits graphically. All right, so let's see if we have another example on this page. And we don't, so we're going to go to the next page. Okay, and now we're going to talk about this discussion of one-sided limits. One-sided limits, we only need to see what the function values get close to as x approaches some value from the right or the left. And again, we have a very different notation here. We have very different notation. This funky notation right here. The difference here is this little plus sign. That little plus sign says that we are approaching 2 from the right. As x approaches 2 from the right, that's what this guy right here means. That doesn't mean positive or negative. All that says is as x approaches 2 from the right, what do the function values get close to? And this little rascal here, this little negative right there, that asks the question, what do the function values get close to as x approaches 2 from the left? So if I look down here, again, I have a graphical limit that I'm going to evaluate these limits. And this one says, what do the function values get close to as x approaches 2 from the right? So what am I doing right here? I'm approaching 2 from the right. I'm approaching 2 from the right. What do the function values get close to? Well, here's the function points, the points on the function. And what do those y values, what are those y values getting close to as x approaches 2 from the right? Well, it looks like those y values, and you are right, are getting close to -1. So we would say the limit as x goes to 2 from the right of f of x is equal to -1. This says, as I approach 2 from the left, what do the function values of f of x approach? So if I'm coming over here and I'm approaching 2, and I'm getting ever so close to 2, ever so close to 2, what do the function values get close to? So here are the points that I'm talking about. If I take these points on f of x, what are the function values? What are the outputs ever getting so close to? Well, they're getting close to this guy right here. They're approaching 1. So this is a demonstration of a graph. I'm going to erase this stuff here so we can see it better. This is the demonstration of a graph where the limit as x approaches 2 from the right isn't the same number as x approaches 2 from the left. These are not the same because 1 does not equal -1. Well, these limits exist. But for this limit to exist, the limit as x goes to just a, not from the right, not from the left. The limit as x goes to a of f of x equals L. Two things must happen. The left-hand limit must go to L, and the right-hand limit must go to L. That's when the limit exists. This particular limit exists. Only if the left-hand limit equals the right-hand limit. And L must be a real number. We will see some instances in a day or two where the right-hand limit and the left-hand limit both go to infinity, but that limits that go to infinity, they do not exist. Okay, so let's go to example 4 and investigate this. I have example 4 here, and I have my graph. Again, this is going to be the graph of y equals f of x. And I'm going to help you out on this graph right here because it has to be a function. So this particular graph should have an open circle right there because it's closed here. So we have a couple open circles, we have a couple closed circles, and we have this graph consists of two line segments and looks like a portion of a parabola. All right, so let's find these limits. Let's go to the limit. The limit is x goes to -2 from the left. So this is what we're doing. We're approaching -2 from the left, and the question is, what do the y values get close to? So here, what do the y values get close to? And it's a good way, as x approaches 2 from the left here, you might take a bug and crawl up the graph, because what's happening to these x values are getting close to -2, and the bug is crawling up the graph. What y value is the bug getting really close to? Well, the bug is getting really close to 4. And let's go with this limit. The limit is x goes to -2 from the right. And now I'm going this direction. I'm approaching -2 from the right. Here's my y values associated with that. And as I approach this, what's happening? My bug is crawling up the graph. And what y value is that bug approaching? Well, golly, that bug is approaching 4 as well. So here I have a case where the left-hand limit does indeed equal the right-hand limit. So I can come over here and say, yup, this limit is x goes to -2 of f of x does exist, and it equals 4. And 4 is a real number. 4 is a real number. And the left-hand limit equals the right-hand limit. So now we can confidently say that that limit does indeed exist. All right, so let's do these. Now, as x approaches 2 from the left, and this thing's got nothing to do with the -2 or negative anything. So let's do this rascal right here. The limit is x goes to 2 from the left. So here's your 2, and I'm approaching 2, getting ever so close to 2, and this is all non-static. It's moving. That's what's one of the most difficult things about calculus, is it's non-static. It's moving, and it's hard to see these moving things on a two-dimensional surface. Okay, as x approaches 2 from the left, where is the bug crawling? I really like the bug idea. And I'm going here 2 from the left. Where is the bug? The bug is going to follow the x's close to 2. And the bug is crawling along the points of the function. And we want to know, where do the y values get close to? You betcha. They get close to 4. Let's go to the other side now, because we want this limit here as x goes to 2 from the right. As x goes to 2 from the right, up here at this bug, and this bug is crawling, crawling, crawling. And what do the y values get close to? Those y values are getting close to 1. So here I have a case that the left-hand limit does not equal the right-hand limit. So I come over here and I'm going to say, ladies and gentlemen, this limit does not exist. That limit does not exist. And I'm going to just make a couple notes about this particular graph. This graph, this point right here, which it didn't really matter, that point right there is -2, 2. That's on the graph, but it really didn't matter for us. It didn't matter doing those limits. This point didn't exist here because it's just 2, 4. It's open circle, it doesn't exist. That point right there is 2, 1. And I just want to put those points out there. They've got really nothing to do. The function value at 2, which is 1, has got nothing to do with this limit. Okay, the limit asks what the function values get close to. And yes, just so happens in this case that the function values do get close to 1. Doesn't matter, though. For this limit, it doesn't matter. And we see here that the point -2, 2 is on the graph. Right there it is. Right there's a rascal. But these limits, where did they go? They went to 4. So we want to be very careful about that. So let's do the next page, and there's going to be 3 examples on this. And I'm going to give you a couple minutes. What I would like for you to do is to pause the video, and what you're going to do on this activity is you're going to graph each of the following functions on the grid to the right and use the graph to evaluate the given limits. And absolutely, ladies and gentlemen, use your graphing calculator if you have to use your graph. These are easy functions to graph, but use your graphing calculator to graph these and see if you can evaluate these limits. You have your textbook. You're going to have 3 examples. Example 1, example 2, and example 3. This is a rational function. This is number 2 is a piecewise function, and number 3 is just a quadratic. You give those a whirl. Pause the video, and give these guys a whirl, because I'm going to, as you pause the video and give them a try, I'm actually going to finish the problems. So let's pause here. Okay, so hopefully you've paused the video, and I have filled these out while you pause the video just to make sure that you could get just to give you some extra practice, since this was an activity. This graph of this function x squared minus 3 was fairly simple, just a parabola. We used that, and then I made note of some points on there because I wanted the limit as x goes to -1 of f of x, and we see that it went to -2. The function values went to -2, and it just so happened that it did equal f of -1. And this property right here will be very important. I believe that's less than 5 or less than 6. If the limit does actually equal the function value, then the particular statement is going to have, this statement right here will have significance. And right now we're really just worried about limits. But the limit as x goes to 0, -3, and the limit as x goes to 2 is equal to 1, and all of those equal to the function value. So there's your answer to that particular one, and the answer to 2 here. This is a piecewise. We did a lot of piecewise. I may throw a review of piecewise and a review of some rational function in a day or 2. But right now, just do your best on these piecewise, because I wanted to jump into the calculus. So this is a piecewise. It has 2 pieces. It has this piece right here, which is a line. This is this piece right here. Okay. And it has this line -x plus 4. And you notice the pieces are not connected, and we have to divide it around 2. And we have to divide it around this x equals 2 right here. And then we ask this limit right here as x goes to 2 from the left. Where does that go? Well, as x goes to 2 from the left, the function value, the bug crawls up to this y value of 3. And as x approaches 2 from the right, what do the bugs do? The bugs crawl up to this y value of 2. And note the solid circle here is because of this greater than or equal to. That's why the solid circle there, and that's why the open circle is there. It's because when x is greater than 2, it's this piece here. Okay, and so that's a review of a piecewise, which we did in pre-calculus. You may have to review those notes. And keep in mind, you can always, this is a discussion that you can have at a Google Meet. Say, hey, Mr. Strasso, I need some assistance on graphing piecewise functions. Okay, but we see what's more important here is that the limit from the left equals 3, the limit from the right equals 2, so therefore this limit does not exist. Alrighty, and then the final one, this rascal is very hard to see. If you put this in your graphing calculator, you're going to have to be careful. The code for this in your graphing calculator, say you put it in y1, you're going to have parentheses around the numerator. Then you have your division symbol, and you have to have parentheses around the denominator. If you don't put this in your calculator like that, you're not going to get the appropriate line. Well, and we will have a review of rational functions, and the graph of that rational function actually looks like this line right here. It looks like this line, but the domain of this doesn't equal 2. So this thing has a point of discontinuity at 2, if you recall from pre-calculus, because I have to lift my pencil up whoop, 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 to graph that. And now we're simply asking the limit as x goes to 2, and as an extra, as a little bit of extra, I looked at the limit as x went to 2 from the left. What does the bug crawl to? The bug crawls to the function value of 4, and as I approach 2 from the right, where does the bug crawl? The bug crawls to again to the function value of 4. So I have the left-hand limit that does indeed equal the right-hand limit. They both go to 4, so I can make this statement: the limit as x goes to 2 of f of x is equal to 4. And note that f of 2 does not exist. F of 2 is not in the domain. This does not exist for this particular, function. Okay, so that is Unit 1, Lesson 1. What's nice about this video is you can rewatch it. You can pause it whenever. And the virtual class will consist of videos for all of these lessons in your interactive notebook, and you will have problems from the digital textbook that are similar to this with each lesson. So good day to you.